we do grain morphology analysis and grain distribution, grain size with scanning electron microscopy. With transmission electron microscopy, we do electron diffraction and imaging. On diffraction, I told you complete details and which are available on the records as well, right? You can check them on the recorded videos. I have explained it. We had long lectures upon these. Regarding I would like to tell you that it is not something unusual or very difficult. When you see an image, don't think that it is something from the sky, right? It is the image of the sample you put there. Here, you see the spaces between fingers. This is the transmitted beam, which appear bright. My hand is stopping light, and that stoppage appears as image on the screen. Whether those radiations or signals are coming from a light source, which are photons, whether they are electrons, whether they are neutrons, whether they are X-rays, and the screen has the capability to shine whatever it touches. So you have a phosphor screen or fluorescent screen. Electrons are not visible, but when they hit the screen of the machine, the screen of the microscope, it undergoes fluorescence. It shows you some shining spots, and those spots are basically giving you images. So with the electron beam coming from up, some of them are stopped by the fingers and the remaining are going down. The transmitted beam and the scattered beam. The difference in intensity is basically showing you an image, right? So that image is not something unusual. You should take it as your homemade thing. In the image, the particles, the grains, the crystals, or whatever they are, they have a specific shape. They may be plate-like, they may be needle-like, they may be rod-like, they may be lathe-like, they may be rectangular, they may be cubic, they may be of different shapes. In many occasions, you see shapes which are not well defined. For example, a grain, if it appears like this, for example, like this, you happily say that this is a cubic shape. But if a grain is something like this, its counterpart is this. Its counterpart is, for example, like this, and this edge is not sharp. This is cube, and this people call cuboidal. Spherical, spheroidal, right? It is not sphere, but like a sphere. है नहीं की तरह है. It is not cube, but something like cube. You can see it. It is well-established terminology that the grain shapes are cuboidal. The grain shapes are spheroidal. If they are sphere, they are cubes, they are rectangles, they are rods, then say that. But if they are not, then you are looking for something which looks like that. And you call them cuboidal, spheroidal, and then if all the grains are spherical or cubic or rectangular or whatever they are, then you say that the grain morphology of this material is like this. If it is not, then you can say that some grains look like spheres, others look like cubes, because you may have a single phase material, you may have a multi-phase material. Even within a phase, the morphology of grains may be different, right? So, interpretation of an image needs two main things. Number one, what you see in the image. Secondly, if you are careful, then do energy dispersive spectroscopy, EDS. EDS is basically the elemental analysis. What electron do? When electron beam comes, they are scattered, they are transmitted, they are backscattered, they are reflected, they are deflected. Such type of interactions occur inside there. Is an electron beam, they behave like the associated de Broglie wave. You know from physics that each and every material particle has an associated wave with it. And the wavelength of that is P is equal to the moment, whatever is that, H by lambda, right? So you associate a wavelength to the particle. So each particle can be considered as a wave as well. When it is a wave, it has a wavelength, right? And when it behaves like a wave, it undergoes interference, constructive or destructive or whatever, reflected, deflected, scattered, right? So from there you get that image, and that image is the constitution of the image comes from different grains, and different grains have different morphology, and you say that the features visible in the microstructure of that material are like spheres, spheroidal, cuboidal, rectangular, or whatever morphology they are. The next thing, which is, if you have done energy dispersive spectroscopy of that electron which hit the atoms of the material also cause shift in the energy levels, and when that electron displaces another electron within the atom or changes its orbit, and it excites it and it goes back, then characteristic X-rays are emitted, and those characteristic X-rays gives you the elemental composition of the sample, right? Characteristic X-rays are giving you the elemental composition of the sample. Now, if you do EDS of these grains or particles, right, they will give you the elemental composition of these grains. The elemental composition of these grains will be, for example, 28 grams or atom or whatever is aluminum, 30 grams is silicon. You don't include oxygen because oxygen is anyway there in the environment. So you wear the aluminum and silicon. Now, if the atomic weight of aluminum divides this, then it gives you 1. And if the atomic weight of silicon divides this, and it gives you 2. So you have 2 atomic weights of silicon and 1 atomic weight of aluminum. So the composition of the final phase will be AlSi2, right? This is the elemental composition. But the material is not a metal. For example, it is oxide. it is ceramic, for example, then Al is plus 2, Si is plus 4 into 2, right? So Al is plus 2, do you remember? Or you didn't go to school before this? What is the charge on aluminum ion? If you don't remember, the simplest thing is Al2O3. It is neutral. When it is Al2O3, right? O is minus 2. It is well known. So it is minus 6. And this is plus 6. Plus 6 by 2. Plus 3. Yes. Right? So this is plus 3. And this is plus 4. Silicon. Plus 3 and 4 multiplied by 8. It's 11. Yes. Right? So here the oxygen, you decide it should be 11 by 2. 11 by 2, no. 11, and it should be oxygen 2. Oxygen is minus 2. So you need minus 11 from here. Right? So it will be 5.5 oxygen. And this is the way that you guess the possible composition of the phase of the grain. This is the way to calculate, but it is always an estimate, right? And I have told you in the previous lectures that when the electron beam is coming and it is here on the sample, the radiations are also coming from here and there. So you can't exactly say that exactly the same number of electrons coming from there are exactly scattered and all of them are coming here. Other outside contribution may also come there, and that is why you are not saying for surety, you are saying estimate. And that is why if you look into the research papers, they say that it may be due to. They never say it is exactly that. It may be due to this. There is more probability or possibility of this. They are not saying it's exactly this because the electron beam is not coming. You can't count electron, that how many electrons are coming. You can't say that if there is a particle here and you are thinking that I am taking the EDS from here, the contribution from this grain is although very small, but it is coming there. So you can't say for surety that this is this, but you say that the detected elemental composition ratio indicate that the composition of the phase is close to AlSi2 or something, right? You say it's close to. Now, who will say it's perfectly? If you do XRD of the same material, then it will tell you about the exact phase. Then you say that the composition, oxide composition calculated from the observation. Secondly, the XRD of this sample confirmed the presence of this phase. Therefore, this particular grain corresponds to that phase. And this is the interpretation of an image. That when you have a complementary technique of XRD, then you do SEM, XRD, and TEM. You combine them, and then you say with some surety that yes, this grain which I observed, this spheroidal grain, this cuboidal grain may correspond to that particular phase. This is the interpretation of image, and I have explained the interpretation of the diffraction pattern in the previous lectures.